So today I'll be talking about origami numbers. Now you probably know what the origami is. It's the art of folding paper. You make patterns on the paper, and if you do that for long enough, you'll get something cool out of it. But today I'm not going to get into too much of that. Instead I'll be talking about origami numbers. Instead of just mentioning origami as like an arbitrary art, I'll say that there are rules that we can follow. There are five of them that just things you can do on a piece of paper that involves folding. So okay, there are two things that can exist on this paper. You have points and lines. Now each fold like that is a line, and I'll highlight these lines with a marker so that it's clear. Now every one of these lines will be like a fold. And so with two of these lines, two of these folds, there's an intersection point. And that is a point. Now here we have generated a point from these two lines. That's axiom 1. You can get a point from two lines. We automatically have this point to work with, basically. Now let's say we have 2 points. We can definitely make a fold through them. Basically, you can generate a line through these 2 points. I'll again highlight that. So these are 2 axioms we have. There are other things, more interesting things we can do, such as a perpendicular bisector. I'll just reuse this piece of paper here. We already have these 2 points and a line, a fold that goes through them. Now we can make a perpendicular bisector of this line segment. And you can do that by kind of aligning these 2 points with a fold. So something like that. You see that the mark of this point lines up with the other one. Make this fold right here. That is perpendicular to the line and divide this line segment evenly into 2. That's a perpendicular bisector that we can make. We can also make an angular bisector. Just say we have these 2 lines that intersect. And say we want to bisect this angle here. We can do that by kind of aligning these 2 lines in the fold. So I'll start with this intersection point because I know that I will go through this point, and then line up this with that, and line up this line with that. And now we have a bisector line that divides this angle evenly into 2 halves. And that's an angular bisector. Finally, this is the 5th axiom. We have a line reflector. So say we have these 2 lines. I want to reflect that line about this line, so that you can imagine it will be somewhere around here. You can do that with origami by, let's see, you can do this. You can fold this first, fold this back. Actually, no, I'm going to fold that first. Fold that along this edge. And that line, where that is, will be the reflected line. So now we have 5 axioms to work with. I'm sure there are more origami operations out there that isn't one of these. But for now, let's just talk about these 5 axioms. So I'm going to define origami numbers as distance between points on this sheet of paper. So you can imagine that we start with a piece of paper. Let's just have 2 points and say that this distance here is just 1 arbitrarily. Because we need something to start with. We need points and lines, and let's define this distance. And so you can make this line. You can make the perpendicular bisector. So if this is distance 1, then this is half because it's a perpendicular bisector. It bisects this line segment. So this is 1/2. And you can imagine that we keep doing this. We apply all of these rules whenever we can. Actually, if we're given infinite time, if we do this infinitely, then we'll get many lines, many points, infinite many of both, and we'll get many different distances. And all of these distances are origami numbers. So let's say this. We say that the origami numbers are just the pairwise distances between all the points we can generate on this paper, starting with these 2 points as like a unit distance apart. And okay, now we have something to work with. We have origami numbers. We know that 1's an origami number. We know that 1/2 is an origami number. We can probably generate more. But now you must be thinking, like, what can we do with these numbers? Now, let's show that addition exists in the world of origami numbers. So, okay, what might addition look like? I mean, since addition is, since numbers are defined in terms of distances, then the addition of distances is just combining line segments together, basically. So if we have this distance, let's call that A, we have this distance, which we call B, then the distance between the endpoints is A plus B. This is A plus B. Okay, so that's addition, but it's not very useful because we know that, like, we're gonna get like all different kinds of lines here and all different points, and they will be scattered all over the place. So what if we want like an addition between, say, this pair of distance, these pair of points, and that? Because they're numbers, and we want to find like the addition between these two numbers. And how we do that? And to do that, we want a way to like move line segments around. We to kind of say if this is already a line, we want to move this segment to kind of here. And that way we can actually get this longer segment that's the combination of these two segments, and then we can call that we have a new origami number that's the sum of these two distances. So let's start with a simpler problem. Instead of moving line segments arbitrarily to some other line, let's start with moving a line segment on this line itself. So we want to move this line segment to somewhere here such that this point is now one of its endpoints. How do we find this point? Now, okay, we can start by doing a perpendicular bisector between that point and this other point we have. So now we know that this distance is the same as this distance. We want to kind of reflect that point about this bisector we have. We'll just say that we have a line that goes to this point because the point is defined by the intersection of two lines. We know that this line must exist somewhere. So let's want to reflect that line about that line. So we will have this intersection here. And you can come to convince yourself that this distance, this line segment, has the same length as this segment. Okay, so now we can move line segments about on the line. And there's a way to move that distance, move that line segment to be on this line so that one of the endpoints overlap. And so now we can actually properly do addition between two arbitrary origami numbers. Okay, what do I mean that we have addition? Because addition is this thing that exists. It's an operation that we've learned about and been using for all our lives. What I mean more rigorously is that the set of origami numbers we have is closed under addition, which just means that take any two origami number we have, add them together, and their sum must also be an origami number. Why is this important? Because I want to get into something that is called a field. And the field is just a set of numbers together with an addition and a multiplication, such that these two operations can work as we expect with the set of number we have. If you want to show that the set of origami numbers form a field, then I have to show that's closed and works nicely under the full operation, which is addition, subtraction, multiplication, and division. We have already shown that the set of origami numbers are closed under addition. Subtraction is an easy one too, because let's say if you want to find the difference between the segment B and segment A, then you can just move this segment A into segment B, and then the rest of the segment will just be the difference in the distance. Multiplication is slightly harder. You can do it with similar triangles. So, okay, if we set up the segments here, because we can move segments around, remember, we can set up like this. So we have one segment with distance 1 here, and a segment with length A and a segment with length B on top of this. Then, if there's a way that we can construct like a parallel line here that is parallel to this side, then we will know that these two, the larger triangle and the smaller triangle, are similar, and therefore the ratio between their respective side lengths are the same. And so here we know that the ratio 1 to A must be the same as the ratio B to wherever this length is, and which results in this larger side being A times B. And so that in that way, knowing that we can kind of move segments around and this construct, we can get A and B. I also need to kind of prove that we can construct parallel lines given the line and the new point. And I will leave that as an exercise to you all. It is definitely possible with these operations. It just takes a bit of steps, and that'll take too long. And that's multiplication. We can also get division by basically the same thing, just using different lengths for this. And you'll also be using similar triangles and ratios. And okay, after that very hand-wavy explanation, we know that yes, we can have all of these operations. We have the 4 basic operations for our origami number. If you apply them, you'll still arrive at origami numbers, basically. Why does that matter? We've shown that it's a field. Why do we care? And that's because a field is effectively a generalization of kind of numbers with certain algebraic properties. And many number sets we already know are fields. The real numbers form a field. The rational numbers form a field. The integers, in fact, don't form a field because we don't get really a good division out of it. And it forms something called a group, which is like a precursor to field, in the sense that we only get addition and subtraction with the integers. The sum and differences between integers are also integers. Groups and fields are the objects of study of this field of math called abstract algebra, which they generalize the numbers we know and are familiar with. And so instead of these very concrete numbers such as the real numbers, the rational numbers, we can kind of generalize their definition to many number-like objects, and we can study like their algebraic structure and properties that we know. And those can lead to new exciting things, and knowing that kind of a set of number forms a field or a group, we can kind of borrow into that intuition for numbers that we are already familiar with, and we can work them more efficiently. We can talk about them in a better sense.
So you said that this is the product of A, B, but it's kind of hard to visualize. So normally when we see A and B here, why is AB not like a parallelogram?
Okay.
Or like the area?
Okay. I think effectively we're talking about slightly different things. So you have a rectangle with 2 sides being A and B, then this area will be kind of imagined as A and B.
Yes.
and that's the area. I think we're okay. So let's consider what these actually are. So A is a length. If you like have to put units onto everything, then like the A here is a unit of length. AB here is something else. It's A and B times like a unit area of 1. And so although we're usually talking about like just numbers, we usually consider these units, but they're really referring to different things. But here we're just talking about like if A and B is numbered, then like this is the A and B number times the length, and we have a unit distance set up. We have this unit 1, and we define it as some distance between two initial points. And so A and B here just refers to the A and B sort of value number.
I see.
Times this distance, this unit. So I guess we're kind of mixing numbers and distance here. So we're crossing domains between numbers and kind of geometric properties.